All right, so let's continue on with the course material. The next chapter is chapter 10, Simple Linear Regression. Unfortunately, the word simple does not mean that it's going to be easy. It just means out of the simple linear regression models, we are working with the easiest one, okay, but not necessarily easy. So, what is linear regression? The gist is that we have a group of variables and we would like to use one or more variables to try to gain information about uh, a response variable, okay? Pretty much the variable that we're interested in. So what we can think about this y, we can think about this as the variable that we're interested in, and we want to use some other variables to try to gain information about this variable. So simple linear regression, it's basically just says um, all we have is two variables. We want to use one variable, which we can just think about as an x variable, to gain information about our y variable. Okay, so the term linear, what linear regression means, um, since I'm on, so linear implies that the relationship between y and the x's, right? So the y is our response variable, the x's are our other variables, which are commonly called covariates or predictor variables or independent variables. Okay, but these x's, the relationship between y and these x's is linear, uh, pretty much right, linear. It's like straight line uh, in beta, right? So notice that the betas, right, we just have pluses, right? They can be multiplied by any amount of x's, but the betas themselves, there's never betas multiplied together. The betas are never squared or logged or anything like that, although the x's can be multiplied, but the betas themselves, it's always beta plus beta plus beta. We can tack on these constants, but the betas themselves are linear. Okay, that's technically what linear means. Okay, so again, I said y is the response variable. Um, these things have multiple names. It can also be called the dependent variable. It can also be called the outcome variable. Um, it's just the variable that we're interested in. And these x's uh, are called, as I said, independent variables, covariates, predictor variables. Okay, a few different words for those, probably some that I didn't even mention. These betas, right? These are parameters. Okay, parameters, and so they're just called regression parameters because we're talking about a regression model. Okay, so they're just called regression parameters. And this epsilon is what's called a random error term. Okay, we'll talk about a little bit more about that later. Okay, so as I said, simple linear regression is the simplest case of linear regression such that we only have one covariate, one predictor variable. So all we want to do is use this x, this predictor variable, to gain information about y. Okay, and so um, ignore this epsilon for now and just look at this. This is nothing more than y is equal to mx plus b, right? And we all know what that is. That's the slope-intercept form of a line. And so that's all kind of linear regression is a line, okay? But the difference between, say, just a regular deterministic model and just fitting this simple line is that in real life there is randomness. Okay, most things cannot be perfectly are not perfectly deterministic. Okay, so a very nice cheesy example is let x represent somebody's weight and y represent somebody's height. So it might be desired to, based on somebody's weight, can we predict or gain information about their height? And I think in general, certainly, right? The more somebody weighs, the taller they're going to be in general, right? Of course, there are always exceptions, but that's what this is for, this epsilon, this random error term. This says, yes, there are exceptions. There is randomness, okay? And that's what accounts for randomness, is this random error term. Because of course, certainly, if you tell me somebody's weight, I cannot perfectly always exactly tell you their height. But I think certainly if in general I try to align that a heavier person is going to be taller, I'm going to be right more often than wrong, right? So there certainly is a relationship between a person's height and weight, although it's not going to be perfect. Okay, so just like I said, this is a line, and so these regression parameters can be perfectly thought of just like a line. This is the intercept, and this is the slope. And they have very important meanings in the context of linear regression, okay? Because like I say, these things, of course, height and weight, that's pretty basic, but this is one of the most common statistical tool used by practitioners, okay? So these are going to be variables that are of interest to someone, and they are going to have very specific meanings, and so these regression parameters are going to be very important to understand. So first off, one of the things that right now we're just kind of saying if, but it's going to be one of the assumptions, is that if the expected value of the error term is 0, then the expected value of y just simplifies to this. And if you recall a long time ago, one of the things that we said was that this expectation is a linear operator, so that the expected value of this plus this plus this is, right, just the expected value of each individual part. And these are just constants, right? The betas are just constants. And one thing that's assumed in linear regression is that the covariates, right, the predictor variables are known, okay? It's assumed that those are not random. Okay, it's only assumed that the y is random. And thus, x is also a constant, and so the expected value of this part is just itself. And we just said the expected value of epsilon, if it's 0, then the expected value of y, which again is our response variable, what we're interested in, is just this. And so in general, that's what the linear regression model tries to do, is it's pretty much trying to model the average value of y for certain x values. Okay, so again, beta naught is the intercept, and so again, thinking about it in terms of the average value of y, the expected value of y, it's the y-intercept, right? So it's the average value of y when the predictor variable is 0. So sometimes this has a very nice interpretation, other times it doesn't. For example, let's go back to our trying to use weight to predict height. Of course, does it make sense to predict the height of a person that weighs 0, right? No, it doesn't. So in that case, the intercept term beta naught would not be useful to think about. Other times it could be, okay? It just depends on the problem. But one thing that will always be of interest is the slope, beta 1, okay? And so it's basically whenever we have a 1 unit change in our predictor variable x, then the change in the average value of y is beta 1. Okay, so for every 1 unit change in x, the average value of y goes, say, up by beta 1. Of course, if beta 1, if the slope is negative, right, slope is negative, then it goes down by beta 1. Okay, so let's look at this little problem here. We've got a waste removal project, and y is moisture control, and x is machine filtration rate. The first time I did this, I turned this into an acronym that I probably shouldn't have, so this time I'll just keep it PC, I guess. So anyway, we've got y and x. So here's our data set, 20 observations, right? For each observation, we have its filtration rate and its moisture, okay? And so we have some crazy units here, whatever the hell this is, and measured in a percent. I think the only thing I don't know is DS, which again, I'm gonna omit my acronym this time. Okay, so we want to use filtration rate in order to try to predict moisture control. Okay, so that's basically the goal. And so with two variables like this, a scatter plot is usually the first step is to see, does there appear to be a relationship between x and y? And notice you will never get confused about which one should I put. Does it matter which way you put it? Yes, it does. Okay, it is always presented as the response variable on the y-axis and the predictor variable on the x-axis. But of course, remember, that's how they're always labeled anyway, and this is pretty universal. Y is the response, so it goes on the y-axis. X is the covariate, the predictor variable. It goes on the x-axis. So we can kind of clearly see that as filtration rate goes up, moisture percentage goes up. Okay, and again, notice that we can't just take one straight line and hit every single point, right? That would be a deterministic model, and that's unrealistic for pretty much everything. What is more natural is that as one goes up, the other goes up, and we can kind of see we clearly have that. Okay, so when you do linear regression, this is basically the gist. You have something like this scatter plot. You've got a relationship between two variables that appears to be linear. And so again, that means straight line. So notice one thing is it doesn't look like there's a huge curve, right? A curve in these points. It doesn't look like the points go up and back down, right? Or some other crazy pattern, right? It just basically looks like they're kind of scattered a little bit, which isn't a pattern, right? But as one goes up, the other goes up. And that's the perfect thing that we look for in linear regression. Of course, one thing I will say, if there is some sort of a pattern, like going up and then back down or a curve, we can actually account for that in a linear regression model, but not in a simple linear regression model, okay? But we will talk about the little bit more difficult cases later. But for now, it looks like that a straight line could be a pretty decent model for this set of data. And again, that's what simple linear regression is. That's all this model is trying to fit a straight line. And so the goal of simple linear regression is to try to fit the best possible straight line through these set of points. And you can think about it probably called the line of best fit in some previous class, okay? But then you might think, well, what quantifies the best line? Okay, technically, there are many different ways that you could mathematically define best, okay? But for linear regression, we will talk about the most common one that is always used um, in order to fit the best, quote unquote, best line through this set of points. Okay, and that's what's called least squares. Okay, least squares is a method to determine what is the best line. Okay, so the goal, it fits the best line by minimizing this equation. Okay, and maybe you're thinking, okay, well, what, that looks crazy. How does that do anything? So remember, y is our response variable, right? Y is just each one of these y values, right? 75, 78, 78 and a half, whatever, right? It's the y values. And this beta naught plus beta 1x, right? Beta naught plus beta 1x, let's go back up. It is the average value of y for that x value. Okay, so it is basically, if we were to have numbers for this beta naught and beta 1, it is what is predicted for this value of y based on the model. Okay, so what we're doing is we're taking each y value and we're trying to look at the difference between that y value and the prediction of that y value based on our model. Okay, and because some points might be above the line and some points might be below the line, if we square those differences, that's what allows, say, a point above the line not to, say, cancel out a point above the line or below the line, right? That we don't want that. So we want to take into account um, distance, okay? So if we take each of these differences between basically the true value of y that we observe and what we might predict based on the model, square those differences, add them up for each data point, right? This sigma notation is the sum from I is equal to 1 to n. Think about our example. We have 20 data points. So take each data point, subtract it from what the model predicts and square it, add them all up, and the way linear regression chooses the best line is by minimizing that. Okay, and of course, what do we want to minimize it? We want to minimize it with respect to these betas, right? Because we want to choose these betas values. So again, choose the intercept of that line and choose the slope of that line, right? This is just a line equation. So we want to choose the slope and the intercept such that the differences between the data points and the line that I'm going to try to fit is the smallest. Okay, and so in order to do minimization, right, we take the derivative, set it equal to 0, and solve. Okay, and not horribly difficult to prove that if we do that, we get these. One thing I'll note, I don't like this notation. I like putting hats on the betas. So here it's saying B naught is basically the least squares estimate of beta naught. I think it's much more commonly used to put a hat on it, okay, to denote that it is an estimate, okay. But these equations here, these are not important for me, okay. I would much rather you understand, try to hopefully understand what's going on. And so once we do this, right, and we get beta naught hat, beta 1 hat, then we have y hat, the predicted value of y, is equal to beta naught hat plus beta 1 hat x. Okay, and so once we have numbers for these, then we actually have a line, right? If I have, right, y is equal to mx plus b, right, and m and b are numbers, then I just have a line. And so for this real set of 20 points, if I do that, then this red line here is the best possible line that I could fit through these set of points such that this is minimized. Again, the squared distance between each data point in the line. Okay, and so just thinking about that, what we're minimizing, if you think about drawing a straight line, a straight vertical line between each point and the red line, right? Just think about those distances. Take each one of the points, right? Each one of the points, look at how far away it is vertically from the line. Take each of those distances and square it so that they're all positive. Add them all up. This line minimizes all of those added squared distances up. Okay, you cannot possibly fit a better line than this to minimize the squared distances between each point in the line. Okay, and that's the gist of linear regression. It is the best line in that way. Okay. All right, so for this data set, we're not going to have time to get into using R ourselves, but this is basically all you have to do. You have to put LM for linear model, parentheses, put your Y variable, which is called moisture in this case, tilde, put your X variable, which is called filtration dot rate, and hit enter. And it spits out beta naught hat, the estimated intercept regression parameter, and beta 1 hat, the estimated slope parameter. Okay, again, he's calling it B0 and B1, which I don't like. But anyway, okay, so once we have those, we can get what's called a fitted regression equation, okay? Sometimes called a prediction equation. It's basically these y hats, right? These are our predicted y values. They're also called the fitted values, okay, fitted. And so we have y hat, the predicted moisture, is equal to 73 plus 0.04 times the filtration rate. Okay? So let's think about what these parameters mean. You need to be able to understand and be able to interpret these values if you were to ever use this. So what does this 73 mean? It means when the filtration rate is 0, right, this term goes away, that's all that's left, then the average moisture, right, average, we're talking about average, is 73%. Okay, this is in terms of percent. Okay, now honestly, I have no idea whether this makes sense in this problem or not to have a filtration rate of 0. I honestly don't know. It may or may not be useful. But what will be useful pretty much always is the slope. So for every 1 unit, and of course we have crazy ass units for filtration rate, for every 1 unit increase in filtration rate, I expect the moisture percent to go up by 0.04. Okay? Yeah, and it is 0.04 of a percent. I was making sure that the units are all right. Yeah, so it's not by 4%, it's by 0.04% because this is in units of percent. Okay, so doesn't look like it goes up by a whole lot, but certainly it goes up. So for every 1 unit increase in filtration rate, the moisture percent goes up by 0.04. Okay, and that's exactly how you should be able to interpret it in the context of this problem. Okay, and so because this is positive, right, even without looking at this graph, right, again, this equation, this is this red line, right? This is the equation of this red line. So even if I didn't have that, I could basically recreate that red line. I know that the y-intercept is 73, and I know that there's a positive relationship, right? The slope is positive between y and x, right? If this was a negative sign, for example, negative slope, then right, we would have points going down like this, right? But of course we don't in this case. I think that's probably a pretty good place to stop. And as I said in the email, I'm going to be looking into, hopefully for next week, having a live lecture at the normal lecture time so that people that would like to ask questions during the lecture can. And I'm hoping that I'm also going to be able to record it, in which case I will put it on YouTube as I've done before so that you can watch it whenever. Okay, so I'm hoping to accomplish that for the classes next week. Oh, while we're here, I'm going to be sending out the next homework and homework solutions again. Homeworks 4, 5, and 6, the ones that were due after this all happened, you get full credit for. Okay, still highly recommend that you practice them. Okay, but you get full credit for them either way. All right, I will see you hopefully for the next lecture.